Since the dawn of man, people have been looking into the skies, curious of what they thought of at the time, an untouchable frontier separated from man for eternity. In 1969, the untouchability of this frontier was shattered with a human spacewalk on Earth's moon. Since then, dreamers, poets, and scientists alike have been preparing for an even greater feat, a manned mission to Mars. But as with any great project, money is of course the driving factor. And with NASA's annual budget of only $17.7 billion, is a manned project even possible? To answer this and many other questions, to Mars or bust, the economics of a manned mission to the Red Planet. To begin, I would like to provide a brief overview of this podcast. The purposes are to analyze and break down costs of different ideas of manned missions, to calculate the net cost of each possible manned mission, and to compare the possibilities and weigh pros and cons of each. I have calculated cost using the same basic method using three main variables, being launch, travel expenses, and equipment. The overall cost is found using this handy formula. C equals L plus T plus E. Cost factors do not include, however, mission control costs, employee salaries, or development costs. Only the mission itself, and none of the side factors are calculated. Also, a side note, I'm assuming that these missions will take place in 2018 because of the close proximity of Earth to Mars. This will hopefully eliminate weird or obscure technology. So, sorry, sci-fi fans, but none of this. Or this. Well, maybe the hoverboard. So moving straight forward, the three possible manned missions to Mars will be an orbital flyby mission, a surface exploration mission, which would be similar to the moon landings, and, of course, finally, a colonization mission in which astronauts would not return to Earth, but rather begin a human colony on the Martian surface. Let's look at an orbital flyby mission, examining some of the pros and cons. Some pros include a low risk factor in that there will be no propulsive maneuvers, no entry into the Martian atmosphere, and no rendezvous or dockings, and of course it will also be a short mission, only approximately 501 days into 2018. And of course, because of simplicity, there's lower cost. Some cons include the fact that there will be no physical touchdown on Mars, nor any tangible specimens brought back to Earth. These factors lead to a low scientific value of such a mission. But let's go on ahead, let's begin this mission. So 3, 2, 1, blast off. To Mars or bust, using the most current Atlas V rocket, which brought the Curiosity rover to Mars, has already cost NASA $185 million. 3 cheers for gravity for this hefty bill, but this is only the beginning. So now we're in space, whipping along towards point B. But Mars, being more than 34 million miles away even at its closest, it'll take us a while, about 501 days as I mentioned before. So the cost of this wait period is what I would like to call travel expenses. So what are travel expenses? Anything used in this 501-day wait. More specifically, food, fuel, necessary living commodities and entertainment, and equipment used specifically for travel. Well, food is very necessary for any manned mission, and thus must be factored into an overall cost. To find this factor, we must use another variables. So, food cost, denoted as F, number of astronauts, denoted as A, and mission time, denoted as T. Quite ironically, food cost equals F times A times T, or, as mathematics likes to write it, fat. So, using the statistics of $50 per meal per day, 2 astronauts for the flyby mission, and 501 days gives us food cost of approximately $50,100. For use later when we're calculating fuel costs, I'd like to also mention that the weight of the food per day is approximately 3.8 pounds, or for the entirety of the mission, 1.9 tons. Yeah, astronauts tend to like to eat a lot, I guess. So, to control the space capsule, the spaceship that they're going to be using to get to Mars, you need to have a command module. Similar but more advanced than the Apollo module, the Mars mission would require an Orion command module, which is the latest and most likely candidate for a manned mission to Mars. But the cost of the Orion command module is approximately $8.875 billion. Broken down, this is about $3.9 billion for engineering costs, $3.5 billion for spacecraft manufacturing, $750 million for sustaining work, $635 million for abort systems, and the Orion module also weighs approximately 23.424 tons, so a major influence on fuel costs. And in order to support a crew without much cabin fever, a deep space habitat must be included in the spacecraft. A deep space habitat for a 501, 502, approximately 500-day mission would be similar to the Destiny Laboratory, which is a laboratory already deployed in the International Space Station run by the United States. To NASA, this is known as HAB-MPLM. Knowing this, the HAB-MPLM deep space habitat costs approximately $1.4 billion and would weigh approximately 16 tons. So another heavy factor to be considered when we're doing fuel, which we're going to do right now. So the cost for fuel is dependent upon the weight of the spacecraft. A study by Ohio University proved that it takes 38 tons of rocket fuel to take a spacecraft to and back to Mars. So this is a spacecraft going to Mars and then returning back to Earth. The Atlas V rocket fuel costs approximately $160,000 per ton, and totaling up the weights for food, the command module, and the deep space habitat, which are really all that we're needed for a flyby mission, we find that the overall weight is approximately 41.324 tons. And then once we multiply the factors together, 38 tons, $160,000, and 41.4324 tons of equipment, we can find that the fuel costs for a flyby mission cost approximately $251.2 million. You can look right on the screen, I don't want to read it, but $251.2 million. So, 501 days have passed and we've returned to Earth. We can make a tally of all we've spent for our flyby mission to Mars. So adding up launch price, command module, food, fuel, and living space, we've spent approximately $10.7 billion. Keep in mind we haven't even landed on Mars, but $10.7 billion. So this ends up being approximately 60.5% of NASA's current budget. Well, it appears it's possible, but hey, US government, can you spare a dime? So now let's look at another possible mission for Mars. The Surface Exploration Mission, or a mission where we send astronauts to the Martian surface, they collect samples, and then return back to Earth. The pros of such a mission would be the allowal to bring back tangible specimens, something none of our rovers currently can do. Other pros include short mission length, lasting just a little bit longer than the flyby mission, at approximately 516 days. And of course, what every nation wants, bragging rights about being able to send men with a physical touchdown. Cons, however, include a larger crew, about 3 to 4 people, as well as a Mars lander would be necessary, and higher risk because of the reliance on 2 spacecraft, the lander and the module. And of course, there will be rendezvous and docking maneuvers, which would be allowing for a smaller margin of error, just making it even more possible for something wrong to happen. So, in considering this mission, let's first look at some similarities between this and the Mars flyby mission. The launch price is very similar, if not the same. Using the Atlas V rocket, it'll cost, again, approximately $185 million. The same Orion command module can be used, and it would still be costing $8.675 billion and weighing a hefty 23.424 tons. And the same HAB MPLM capsules can be used for the deep space habitats, costing $1.4 billion and weighing 16 tons. And finally, the same statistic of 38 tons of fuel per ton of cargo can be applied since we're going both to Mars and coming back to Earth. So, of course, food is very necessary for any manned mission, and thus must be factored into the overall cost, just like we did with the flyby. So we can use the same variables that we used for the flyby mission, which would be denoted as F, denoted as A, and denoted as T, for food cost, number of astronauts, and mission time. So, ironically, again, food cost equals F times A times T, or fat. So, using the statistics of $50 per day, 4 astronauts, and 516 days, this gives food cost at approximately $103,000. For use later and fuel costs again, the weight of the food per day is approximately 3.8 pounds, and factoring this in, we find that for the entirety of the mission, it would be 3.3 tons of food. So one major difference between the Orbital Flyby mission and the Surface Exploration mission would be the requirement of an Earth Return Vehicle. Now, what is an Earth Return Vehicle, or an ERV? Well, it's very similar to the Lunar Landing Vehicle. Actually, the Lunar Landing Vehicle, or the Lunar Lander, was an ERV. So it would be the Mars Earth Return Vehicle, and it would be the capsule in which men would leave the primary spacecraft and then venture to the surface of Mars, and then use the spacecraft to return back to the primary spacecraft and return to Earth. So the Altair lander, an experimental lander from NASA right now, would be the one most likely for a mission to Mars. It would cost approximately $7 billion when we analyze the range of costs and use geometric means, and then also weigh about 50.5 tons. Once reaching the surface of Mars, the astronauts would need several pieces of equipment. Spacesuits and oxygen are a given, costing approximately $8 million for the spacesuits and $3 million for oxygen. A Mars roving vehicle similar to the lunar roving vehicle for ground transportation would also be needed, and this is because we want to be able to explore the largest surface area of Mars while we're having astronauts be on the planet. So this roving vehicle would cost approximately $219 million. Additively, the cost of equipment for Mars would be approximately $230.2 million, but actually has negligible weight when we consider it for fuel. Using the same formula from the flyby mission, we can make some calculations of fuel costs for the surface exploration mission. So once we add up all the weight of the different equipment that we've been using, including the Orion command module, the landers, and the deep space habitat, it comes to approximately 92.62 tons. Once we put this into the return trip formula, in which it takes 38 tons of fuel and costs $160,000 per ton, we find that the cost of fuel for this mission would be somewhere around $563.5 million, more than $500 million just for fuel. Adding up the costs for the launch, travel expenses, and equipment, we can find the total cost for the surface exploration mission to be approximately $17.8 billion, or a little more than 100% of NASA's $17.7 billion budget. Well, at least we can dream about this mission. But there's still one more type of mission to consider: the idealistic mission, colonization. A colonization mission would be the most difficult and risky mission on the table, so we must carefully evaluate the pros and cons. The pros of the colonization mission will be very high scientific and explorational value. It would also be an important step in space exploration because it would be the first interplanetary mission. And of course, bragging rights, as the explorers of the past would have said, we want to go there because it's there. But some cons include extremely high risk, as once again it would be our first planetary colonization mission, and we as humans have never done anything close to this scale. Also, an undefined mission length and a large crew size would cause a very high cost and pose other cons for such mission. The first difference between this mission and the other two previously discussed is because of the large number of people, approximately 24, and the large amounts of equipment needed. 2 separate rocket launches, 2 separate command modules, and 2 separate deep space habitats are needed. So, going straight to the launch price is $185 million times 2, which comes to approximately $370 million. The astronauts' travel commodities would be much the same as for the surface exploration missions and the orbital flyby missions, except doubled for the 24 astronauts and only consisting of 250 days for the one-way mission. So altogether, food, 2 Orion command modules, 2 deep space habitats, and 2 Mars landers comes to approximately $35.5 billion, and the weight is approximately 191.2 tons. Yeah, very heavy, very expensive. So, the equipment for a colonization mission will be much more expensive than either other missions before, and this is because simply these people won't be returning to Earth. They have to be able to set up their own colony on Mars. So, already factoring in oxygen in spacesuits, the colonizing astronauts would need 4 colonization shelters, automated water machinery to synthesize water from the available resources on Mars, agricultural commodities in order to grow their own food and keep plants on Mars, and communication systems to keep in contact with Earth for the entirety of the mission. And once we factor in all of this, we find that it's approximately $21.9 billion and weighs approximately 25 tons. So now that we know the weights of most of the equipment that we will be bringing for a colonization mission, we can calculate the approximate cost of fuel for this mission. Since there will not be a return trip for this mission, there would only need 7 tons of fuel per ton of equipment to get us to Mars. We're not going back, so we don't need the 38 tons like the 2 former missions. Now, for calculating this one-way mission, we multiply the weights of the equipment, which are approximately 216.25 tons, by the number of tons of fuel needed to get to Mars, 7, by the cost per ton, and then multiply this by $160,000, the cost for every ton of rocket fuel. With this formula, it gives us the price of fuel to be approximately $242.2 million. Adding up the costs we found for launch, travel expenses, fuel, and equipment, we found that the startup cost for a colonization mission would be a staggering $58 billion, or 338% of NASA's requested budget for this year. Now, we can dream about this as dreamers and poets often do, but in the foreseeable future, the cost of colonization is too high for what we're going to get out. Reviewing back, we've considered 3 separate types of manned missions to Mars: orbital flyby, surface exploration, and colonization. Looking at the costs, the flyby mission would make the most economic sense, still costing an outrageous 60.5% of NASA's budget. But hey, this is better than the colonization cost at $58 billion, or 338% of NASA's budget. So, orbital flyby, possible, maybe with some help from private organizations like SpaceX or Virgin Galactica. Surface exploration? Probably not, due to its incredibly high cost, and probably a no-go for colonization. You already know why there. But in coming years, with ion drives and cheaper spacecraft, surface exploration, or maybe even colonization, could be achieved. So, dreamers continue to dream, thinkers continue to think, and maybe, to Mars or bust. Signing off, this is H&W Podcast. Thank you.